Okay, good evening, or good morning. Welcome to Twitter Math number 11. So yesterday on Twitter, James Tanton put this fun little equation up. It's one of a neat numerical identity. It says if you start at 1 and add up the cubes of the integers, that sum turns out to be the square of the sum of the integers you're summing up. And he asked for a geometric interpretation of that, which is actually pretty neat, I think. And then last night I was reading rereading, really, it's one of my favorite books, Ingenuity in Mathematics by Ross Hansberger. And I came across the same problem going in a different direction, and I wanted to just share that with you because I think it's really neat. And then I want to talk about one unsolved problem that sort of relates to this. So we have this sequence, which is fairly well known, but still pretty cool. And in the 1800s, the French mathematician Liouville proved a more general idea. Take any positive integer, so for example 6. Write down the divisors. So the divisors of 6 are 1, 2, 3, and 6. Now, for each of these divisors, write down the number of divisors of each of these divisors. So 1 has 1 divisor, 2 has 2 divisors, 1 and 2. 3 has 2 divisors, 1 and 3, and 6 has 4 divisors, and we wrote them down here. Now this sequence of numbers here has the same property. The sum of the cubes is the square of the sum. 1, 2, 2, 4 squared, which is 9 squared, 81, is 1 plus 8 plus 8 plus 64. And that's pretty neat. Let's do one other quick example, just to show you that it really does indeed work. And the proof actually isn't that hard. It's in this book, or it's in my Ingenuity in Mathematics book, but it's also not that hard. You show that if two numbers satisfy that property, then their product does. So let's take 20, for example. So the divisors of 20 are 1 and 20, 2 and 10, 4 and 5. There's 6 of them. And then we can count the divisors of each of these numbers. 1 has 1, 2 has 2 divisors, 4 has 3 divisors, 1, 2, and 4. 20 has 6 divisors, we just wrote them down. 10 has 4 divisors, 1, 2, 5, and 10, and 5 has 2 divisors. So according to Liouville's generalization here, these numbers cubed, so the sum of these numbers cubed, 1 cubed plus 2 cubed plus 3 cubed plus 2 cubed plus 4 cubed plus 6 cubed should equal 1 plus 2 plus 3 plus 2 plus 4 plus 6 squared, and you can just check this for yourself that they do. So that's really neat. And the unsolved problem I wanted to mention that sort of relates to this, but I think is one of the neatest unsolved problems, is relating to the inverses of these. So if we sum up 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus all the way to infinity forever, turns out this is pi squared over 6. And Euler actually figured out any even power, what the sum was. He wrote down a formula. But nobody, 1 squared, 1 cubed, 1 over 2 cubed, plus 1 over 3 cubed, etc. People know this sums to some number. They know that number is finite. In fact, it'll be less than pi squared over 6 because these numbers are smaller numbers. But nobody knows how to write down a closed formula or closed form for this number. So it's interesting that the sum of the square or the cubic integers have such an easy formula, actually involving squares, but the sum of the inverse cubes, all the way up to infinity, is actually unknown. I found that pretty fascinating. This has always been the problem I wish I could figure out the solution to since I was a kid, but never have. Okay, great. Thanks for watching.